Hey folks, I've got a conservation momentum example with you, and it's going to be an inelastic collision. Okay, so in the previous video we had explosions. That's where two things started together and ended apart. Well, inelastic is the opposite. The two things will start apart and end together. So here's my example. And this example, by the way, we're going to talk some big picture ideas near the end here. So this is one to really pay attention to. So this example is called the ballistic pendulum. So imagine you have a block of mass m hanging from a string. And let's say you fire a bullet with mass little m into it. Okay. The bullet will embed itself in the blocks like so. And then the block and bullet combo will go to some new height. So that'll be m plus m before they stop. So there's your height h. Okay. So it turns out if you're given numbers for big M and h, okay, and the height, or I'm sorry, and the mass of the little guy, you can figure out with what speed the little guy hit the big guy. So we call it impact velocity, or for if it's an actual firearm, it'd be muzzle velocity. Okay. Now I'm going to throw data up here, but we're going to only use it at the very end of each part of this problem. So let's say the mass of the bullet is 10 grams. And let's say the mass of the block is 1 kilogram. And let's say the height that block achieves is 5 meters. Okay. Now, in a real ballistic pendulum, like that's actually used to be a device that law enforcement would use to calculate muzzle velocity. They'd make the mass of the block much bigger, so it wouldn't go nearly as high. But we're going to go ahead and use these numbers. All right. So how do we figure out the velocity of the bullet before it strikes the block? Okay, well, a common misconcepted way to do this is to try to do the following. I will have people they'll say, oh, well, the bullet has some kinetic energy before it hit the block. And that all turned into potential energy at the top here. So they'll set 1/2 mv squared of the bullet equal to the sum of the m's, gh, of the block. And it turns out that they'll get an enormously wrong answer. It'll be off by a huge factor because they're using conservation of energy. And it turns out in this interaction, energy is not conserved, not even close. Okay. So it turns out this is going to be a two-step problem. So let's call location A before they collided. Let's call location B the right after the bullet has embedded itself in the block and the bullet block combo is now moving together. And then we'll call location C when they stop at the max height. Okay. So let's go from A to B first. So when we go from A to B, okay, we have two objects interacting, bullet hitting block. And then therefore the block will hit the bullet. The total force of the block bullet system will be 0, and therefore momentum will be conserved. So the total momentum at A is going to be the total momentum at B. Okay. At A, that's before the collision, you had the bullet, which was M, moving at some velocity. We'll call that V naught. And that's what we're trying to solve for. We're trying to get V naught. Right after they collided, well, now they're stuck together, moving with the same velocity. So I'm going to add their masses together like so. And then I'll call the second velocity V. I don't know what that is either. So here's the problem here. We have two unknowns. We don't know V naught, nor do we know V. So we need to do something else to solve this problem. Well, that's where you go from B to C. Now, when we go from B to C here, that is now one object moving from one point to another. So there, we're going to use conservation of energy. U at B plus kinetic energy at B plus any work done by any non-conservative forces equals U at C plus kinetic energy at C. Now let me pause here. Here is the big picture, very important. Open those ears and pay good close attention. If you are studying one object at one spot in its motion. So for instance, let's say we're looking at a roller coaster and you want to know something about when the roller coaster is at the top of a loop-de-loop and you're only looking at that one location only. What general idea do we use? Well, it's not conservation of momentum and it's not conservation of energy. You're going to use Newton's laws of motion, primarily Newton's second law. So you're going to draw an FBD, and you're going to do net force equals ma. Okay. On the other hand, if we have one object moving from one point to another. So for instance, let's say we're studying that same roller coaster as it moves from the top of its first hill to the bottom of its first hill. So that's one object moving from one point to another. Well, then we're going to use conservation of energy, which is what we have when we're going from B to C here. We have one object moving from point B to point C. And now in this unit we have, or this chapter, we have a new tool in the toolbox. If you have multiple objects interacting, so in this case, the bullet and the block, then you use conservation of momentum. So when two or more objects interact with each other, you use momentum. So for analysis, big picture, we use net force equals ma for one object in one spot. We use conservation of energy for one object moving from one spot to another. And we use conservation momentum if we have multiple objects interacting. Okay. In this problem, we got to do two of those three. We don't have a choice. So if we look at B to C now, assuming we call the bottom of the swing zero height, there's not going to be any potential energy. There is a non-conservative force acting as the thing swings from B to C, and that's the tension in the string. That's our non-conservative force. But it ain't doing any work because it's perpendicular to the motion at all points. So that's a zero. When the thing gets to the top of its path, it's no longer moving, so it doesn't have any kinetic energy. So we get a pretty simple equation here. So we got 1/2 the combination of the masses times v squared equals the combination of the masses, gh. Okay, well, first off, the gm's drop out, so we cancel that. And we get the velocity is root 2gh, which probably looks familiar to you folks. Okay, so that's the velocity that goes right here. Okay, that's the velocity the two things had right after the collision. So then I'm going to put that in right here. So now I got little m v naught equals little m plus big M, and then root 2gh. Okay, so in that equation, I've got everything in that equation saved for what I'm trying to solve for, which is v naught. Now I'll go ahead and write this out. So little m plus big M, root 2gh over little m. Okay, now at this point, if you had numbers, which we do, we'd plug them in. So just for fun, we'll go ahead and do that. So we got little m, which is 10 grams, which is 0.01 kilograms, plus the block, which is 1 kilogram. Root 2g is 9.8, and h is 5, all over the little mass, which is 0.01. And if you plug and chug these into your calculator, you get almost exactly 1,000 meters per second. Okay, which would be a fast bullet, be a high-powered rifle at the very least. Okay. Now, there's a part 2 of this question. Okay. Part 2 is, and you'll see wording similar to this in some of your problems. Okay. What fraction of energy is lost? Because we said energy is not conserved. Okay. What fraction of energy is lost when the bullet embeds itself in the block? Okay. So if we want fraction energy lost, okay, so we're going to take the amount lost, so that would be the energy final minus the energy at the start. That's the amount you lost. Okay, it's going to be negative because you're losing it. Okay, divided by the total energy we started with. So the change in energy over the starting energy. That's the fraction we lost. Okay. All right, so the energy at final was the kinetic energy. Now here we're going to do some algebra. We're going to leave this in variable form, so I'm not going to use numbers. I'm just going to use letters. So the energy final was the kinetic energy of the bullet block system, which was 1/2 little m plus big M velocity squared, which was 2gh. The velocity was root 2gh. I'm squaring it, so it's 2gh. So that was the energy I started with. Or ended with, minus the starting energy, which is simply that of the bullet, which is 1/2 little m, and then our expression for that velocity was this crazy stuff here. So I've got to square all of that. So I'll square the little m plus the big M. We have a 2GH, okay, and then over, there's a little m squared. And this whole thing is over, the same thing over again. 1/2 little m plus big M squared, 2GH over little m squared. Now, luckily for us, a lot of this stuff's going to cancel. So the halves all cancel. Let's start with that. One of the little m plus big M's cancel. The 2GH's all cancel. 2GH, 2GH, 2GH. And then in these fractions here, one of these little m's cancels. So there's just an m down there. So this guy and that guy. So now we got a lot canceled. Now this first term, please do not put a 0 there. It is now 1. We divided everything out and it's 1. So we have 1 minus, we end up with little m plus big M over little m divided by the same thing. Little m plus big M over little m. Now I'm going to multiply the top and bottom of that big fraction by the m, and I get the following. Little m minus quantity, little m plus big M over little m plus big M. Up in the numerator, little m minus little m is 0, and we have a minus big M over little m plus big M. Okay, that's the fraction you lost. If you wanted a percent out of that, you just multiply it by 100. For this one, for fun, let's go ahead and calculate this. So the big mass was 1 kilogram, and we had a 0.01 plus 1 here, and you get 0.999, and it's negative. In other words, you're losing 99.9% of your energy. Where did it go? Well, when that bullet struck that block, that energy turned into heat. So if you had tried to use conservation of energy to get from A to C, you would have been off by a factor of 99.9%. So that's not good. So yes, you're losing a lot of energy due to heat. So again, there's a lot here, but the biggest thing you could leave this with is the following. If you look at one object at one location, you're probably using Newton's law, especially second law, to analyze the object at that one spot, drawing an FBD and so on. If you're looking at an object going from one point to another, a single object going from one point to another, then you're going to usually use conservation of energy to analyze it. If you look at more than one object interacting, for instance, when the bullet hits the block, then you're going to usually use conservation of momentum to analyze that situation. So I hope that was helpful, and have a good one.